Alright, hello. It's time for weekly contest 201. Bi-weekly contest. Bi-weekly contest 32. In this video, I'll be doing the problems and then explaining my solutions. So, let's go. Hello, now I will be explaining the problems from Biweekly Contest 32. I didn't do so well in this contest because I was a bit slow on the first three problems and I didn't solve problem 4. But now I figured out how to solve problem 4, so I'll be explaining all 4 problems. Problem 1, kth missing positive number. Given an array R of positive integers sorted in strictly increasing order and an integer k. Find the kth positive integer that is missing from this array. Okay, so we know that k is going to be less than or equal to 1,000. We can just loop through every integer starting from 1, and if the number is not present in the array, then we can increment our missing number count, and then once that missing number count gets to k, we know that we've had k missing numbers, and that our current number missing tracker is the final answer. So it's pretty simple. This is a brute force algorithm. It requires a little bit of thinking, I guess, a little bit of logic, but for the most part, it's simple and straightforward. Problem 2, can convert string in k moves. Given two strings s and t, your goal is to convert s to t in k moves or less. During the ith move, you can choose any index j from s such that j is between 1 and the length of s, and j has not been chosen in any previous move, and shift the character at that index I times, or you can do nothing. Shifting a character means replacing it by the next letter in the alphabet and wrapping around from Z to A. Shifting a character by I means applying the shift operations I times. Remember that an index J can be picked at most once. Return true if you can convert S to T in no more than K moves, otherwise return false. So this problem, the statement was a bit confusing for me, so I had to read it over a few times. And at first I even misunderstood it and coded a wrong solution. So I would suggest you read the problem again to get a full understanding. So basically, we're going to perform as many shifts as we need, and each shift we can only shift it by a unique value each time. So that's the j has to be unique. So if we shift a letter, then we have to make sure that we don't use that shifting amount in the future. How we do that is first we have to make sure the string lengths are the same, because applying shifts, applying moves doesn't change the length of the string, and I got caught out by this. That's why I had one bug on this, but we have to make sure the string lengths are the same, and if they're not, then it doesn't work. And then for every position, every letter position in the strings, we have to count how many shifts we need to make. And this is pretty simple. We can just use the ASCII integer representations of each letter, and since they're all lowercase, we don't need to worry about any cases. We just need to find how far we need to shift each letter. If it wraps around, that's a different case from when it doesn't wrap around. But it's pretty simple to find how many shifts we need to make for each position in the strings. If that shift has already been used, then we increase it by 26. If this has been used, then we increment it by 26 again, because incrementing a shift count by 26 is the same thing, because you just wrap around one more time, but it makes that value of j unique. And we keep doing this until we get a unique value of j, or until this value of j exceeds k, because over here it says that during shifting we can only make k shifts at most. So we need to make sure that it's at most k. But if this is impossible, if there's no unique shift value that is less than k, then we can't do it, and then we have to return false. That's this bit over here. But also, finding this can be pretty difficult because k is at most 10 to the 9. So if we just keep incrementing by 26, that could give us a TLE, time limit exceeded. So we do this using binary search to find the lowest value of j that we can use. After all that, we have accumulated an array of all the values, all the shifting values that we need to use. And if this array contains all unique values, and all of its elements are less than k, then we know that all the shifts are valid, because the problem says that they need to be unique and all less than k. So at the end, if our required shifts satisfy those, then we know we're good, and we can just return that. Yeah, and that's it. I think for this problem, it just requires a bit of thinking, not really any special algorithms. Problem 3, minimum insertions to balance a parentheses string. Given a parentheses string S containing only the characters left parentheses and right parentheses, a parentheses string is balanced if any left parentheses must have a corresponding two right parentheses. Left parentheses must go before the corresponding two consecutive right parentheses. These are balanced, and these are not. You can insert the characters left parentheses and right parentheses at any position to balance it if needed. Return the minimum number of insertions to make the string balanced. There's a lot of work here, but the idea is basically that if at any point you have enough right parentheses to balance out the left parentheses, then you remove them basically, and we keep account of how many lefts and how many rights we've seen so far. And then at the very end, if there's more left parentheses left that we haven't balanced out, then we just insert those. That's over here. But also in the middle, if at any point the right parentheses outnumber the left parentheses, we know we need to add some left parentheses because those right parentheses aren't going to get any more left parentheses to balance them out. And that's described over here because they must go before. So if we have two consecutive right parentheses that don't have any left parentheses to balance them out, we need to add a few. And that's described over here. But also there's a special case. So if there's any right parentheses that are followed by a left parentheses, any future left parentheses cannot use any right parentheses on the left of our current index, because this rule says here that they need to be, the right parentheses need to be to the right of the left parentheses. So we need to make sure if we see a left parentheses, then we need to balance out all previous right parentheses because we can't balance them out any further. And yeah, that's it. That's basically just a lot of casework. I think I've said all the cases. Okay, I think this is just, it requires a bit of logic, no special algorithms either. Problem 4, find longest awesome substring. Given a string S, an awesome substring is a non-empty substring of S such that we can make any number of swaps in order to make it a palindrome. Return the length of the maximum length awesome substring of S. Okay, so this problem's kind of like twosome, but it also requires bit masks, and I will explain why that is. So first thing to note is that if we keep account of how many of each digit have appeared so far, if we make sure that for any substring that the counts of those digits are going to be all even, with at most one of them odd, then we can form a palindrome without substring. And we can do this using prefix sums. So we can just keep a prefix sum of the counts of each digit, and then to find the counts of digits in one substring, we can just do a prefix sum range query. Yeah, you should get familiar with prefix sums because they're super helpful in contests. And at this point, this is where bit masks come in. Okay, we're definitely going to need a diagram. Okay, so for every point in the array, we maintain a prefix sum, which is the counts of each digit. So in this example, 324, 324, 2415. So if, for example, we're at this point, then the third index is going to be 1, the second index is going to be 1, the fourth index is going to be 1. These are all going to be zeros. So this is going to be our prefix sum. And notice that we can essentially reduce this to only odds and evens, because if we have two 2s, that's the same as having 0 2s. Because for a substring to be a palindrome, we only need it to have an even count of each digit. And even means we can take everything mod 2. So we're only going to have zeros and ones in our prefix sums, which counts, again, the occurrences of each digit so far. So, for example, if this is our prefix sum, we can turn this into an integer. We can turn this into a 10-bit integer because it's only ones and zeros. And a motif, I guess, in competitive programming is that if you only have a string of ones and zeros, it's better to store it in an integer than in an array, because an integer is like only the bits. It's only the bits. But an array might have more stuff, and it's easier to work with an integer than with an array. But also for integers, you need to like work with bit manipulations, and I highly suggest that you study bit manipulations. Okay, so at this point, we have a way of describing our prefix sum in an integer. And this helps because at any point, if we look at our prefix sum, as I said before, we're gonna need another prefix sum such that their difference is gonna be all even, because that says the substring in between is only gonna have even occurrences of each digit. It can have one odd digit. I'm gonna handle that case later. So we need this subtracted with another prefix sum is equal to all zeros, and this will only happen if all of them are the same. So we need these to be all the same, right? Because only if we have, I'm repeating myself. Anyway, okay, if we have two prefix sums that are the same, will their difference be all even? That's this part over here. If our current prefix sum exists, then we want to find the leftmost previous prefix sum that has the same values. Okay, but also we need to consider that one of them could be odd. So for each of these, we turn it off or we switch it, and that signals that we can have one odd. Because when we take a difference with the previous prefix sum, that says that one of them can be a 1. And that's what we do over here. This line basically shifts that bit to be odd, and then it compares it if it exists. This is possible because this is a 10-bit integer, so we only need to shift 10 bits. And that is totally doable, because 10 to the 5, if you have a small coefficient like 10, that's totally going to work. Yeah, so I guess that's it. Ideas for this problem are going to be prefix sums, bit masks, and the two-sum problem. The two-sum problem comes up quite a bit, so I'd suggest you take a look at the two-sum problem. You can find it. It's the first problem on LeetCode. Yeah, I highly suggest you take a look at this problem. The normal solution is n log n, or on. The bash solution is on squared. So I highly suggest you take a look at this problem because it contains an idea that is very much applicable to other problems. So yeah, that's it for Biweekly Contest 32 explanations. I hope these explanations helped you, and thanks for watching. I'll see you in the next video. Goodbye.